Calculus Math 11. Dance. Dance. Clap your hands. Today, section 1.5, the infinite geometric series. Consider the following two geometric series. On the left, 6 plus 3 plus 1.5 plus 0.75, and on the right, 6 plus 12 plus 24 plus 48, and so on. And let's calculate the sums of the partial series here. The first sum is easy to obtain, as well as the second sum and the third sum. But let's carry on from here, and I'll show you a little trick that you can do with your calculator. Go up here into the y equals menu. You may have an equation already in there. I do. I'm going to clear it out. And what I want to do is use the formula to calculate here. So Sn is equal to T1, which in this case is 6, times, I'm going to put brackets, we need to go with r to the power of n. R here is 0.5. Now I'm not going to actually use n as my exponent in this case. I'm going to use to the power of x, and then minus 1. Close that bracket. And all of that is going to be over r minus 1. And of course 0.5 minus 1 is negative 0.5. And we'll close that bracket up for the denominator. I'm not going to graph this. I want to look at a table of values. Before I go to the table of values, I want to check my table settings. And you can see my table is currently set to start at value of 0 and have changes of increments of 1. I like the increment setting, but I'm going to change the table start to a value of 1. And now I'm going to go over and look at the table of values. The sum of the first term, obviously, 6. Sum of the first two terms, 6 plus 3, 9. First three terms, 10.5. First four terms, 11.25. First five terms, 11.625. And so on. And we can keep scrolling on through here, and we can see that the sums are still increasing, but not by very much. Not by very much at all. In fact, here at the 13th sum, we're already at 11.999. So let's just record a few of these underneath the original series. But let's compare this to the series on the right. We'll go back in here, and we will change our equation. 6 times, now our r value is 2, so 2 to the power of x minus 1 over, and if we're doing r minus 1, that's just 2 minus 1. So we can just leave it at this, because it's just going to be over 1. And let's go again back to that table of values. And you can see here, the first sum is 6, the second sum is 18, third sum 42, and so on. But these sums, rather than slowing down, seem to be getting larger and larger, so by the time we get to the 13th sum, we're up at 49,146. The first series getting closer and closer to a value of 12, well, the sum of the second series is really going off to a value of an unlimited value, to infinity. So what we would say is that the series on the left is a convergent series, since the sums are getting closer and closer to 12 as n gets larger. On the right, what we have is a divergent series. A divergent series is one whose value, as the n value gets increasingly large, is impossible to calculate. It just keeps getting larger and larger and larger itself, also going off to infinity. But what is it about the first series that means we can calculate its sum? It's the r value. In the first series here, r is less than 1, and this r value causes each of the terms of the sequence to get closer and closer to 0, so that the sum of the series ends up converging to a single value. In the series on the right, where the r value is 2, the terms are getting larger all the time, and as a result, the sum keeps getting larger and larger, diverging. Let's consider the formula once more for the series on the left. The real question here is what happens in this formula as n gets increasingly large, as n goes towards infinity. Well, let's just consider 0.5 to the power of n, and let's go back to the calculator and see what happens as we increase the value of n. We could start off by saying 0.5 to the power of 6. And then let's consider something like maybe 0.5 to the power of 12. Wait a minute. What does that mean? 2.44 and so on, e negative 4. Well, this is your calculator's way of doing scientific notation. And what it really means is 2.44 and so on times 10 to the power of negative 4. Or in other words, 0.000244 and so on. Let's try 0.5 to the power of 50. 8.88 e negative 16. 8.8 times 10 to the negative 16. As n is increasing, r to the power of n is getting closer and closer and closer to 0. And considering that we actually haven't really made n all that large yet, it's only 50, I think we're going to find out that as n goes off to infinity, we will get even closer to 0. Let's try one more here. Let's try 0.5 to the power of 325. 1.46 times 10 to the negative 98. Put 97 zeros after the decimal place before any of those digits show up. The limit of 0.5 to the power of n, as n is approaching infinity, is equal to 0. So if we take this back into the formula, let's see what happens. So taking that back into the formula now, we can replace n with infinity, and since 0.5 to the power of n as n approaches infinity is equal to 0, we've got 6 times negative 1, which is negative 6 over negative 5. And if you check on your calculator, it's just 12. So if we apply this back into the geometric series formula, where t1 can be any value and r can be any value actually between negative 1 and 1 other than 0, first we can say that r to the power of n, as n approaches infinity, is equal to 0. And so we have t1 times negative 1 over r minus 1. And so we have negative t1 over r minus 1. And just to tidy things up a little bit, I'm going to change the order of the terms on the bottom and factor that negative 1 through the top, giving me the final version of the formula for any infinite geometric series. S infinity is equal to term 1 over 1 minus r, and here's the crucial bit, where r must be between negative 1 and 1. One of my favorite questions, the bouncy ball question. What is the total vertical distance traveled by the ball, up and down, added all together, if it always bounces back to 80% of the height it fell from? Technically, if this is some kind of perfect ball in some perfect universe where it can keep bouncing back to 80% of the height it fell from, it will never stop bouncing. What's the total distance traveled by this ball? What I like to do is consider a little diagram like this. Have the ball drop down, back up to 80 centimeters, down, back up to 64 centimeters, down, back up, and so on, always bouncing back to 80% of the height from which it fell. And what I do in this question is I ignore the initial drop, and I only consider from this bouncing point at the bottom and onwards. I will include this eventually, but for right now, I'm going to go onwards from here. From this point, the ball bounced back up 80 and down 80, meaning it traveled a total of 160. And then it bounced up 64 and down 64, meaning a total of 128. And so on. And if you check it, 128 over 160 still has an R value of 0.8. So what I'm going to do is I'm going to let T1 equal 160. And I'm going to calculate the infinite series in this case. T1 over 1 minus R. So 160 over 0.2. 800. But of course, we ignored the initial 100 that it fell here in the first place, so actually the total distance is 800 plus another 100, 900 centimeters traveled. What is the perimeter of all the squares in the drawing below, where the side length of each square is half of the larger square? And so on to infinity. And in this example, I'm going to say that the side length of the outer square is 4 centimeters. Well, the perimeter of the outer square, of course, is going to be 4 times 4, 16. And the perimeter of the second square, 8. And the perimeter of the third square, 4. And so on. I actually want to take those numbers and add them all up. 16 plus 8 plus 4, and so on, off to the nth term, where n is going to infinity. Sum of the infinite terms is the first term over 1 minus r. We have 16 over 1 minus 1/2. This is 16 over a half, or in other words, 16 divided by a half. I don't really like dividing fractions, so I'm going to make it 16 times 2, which is 32 centimeters. The sum of all of the perimeters suggested by this diagram is a total of 32 centimeters. And now here's one more for you to try on your own. Remember, until next time, keep your pencils sharp, and I'll see you in class.